Okay, so we're at the home run stretch, basically the last lap of your A2 syllabus. It's a pretty long syllabus. So this is the remaining about 1/3, which consists of the more modern version of physics. So I like to call this modern physics because we will have basically quantum. And quantum physics, your focus is studying three main experiments. Okay, three main experiments to tell us that things behave very weird at the quantum scale. When you see the word quantum, it just means very small. So we're talking about around the size of an electron. Okay, so we're not talking about like you or me or a ping pong ball. We are not quantum material, so we're going to look at very small. And then in 23, we're going to look at nuclear physics, which is also things that are very small. All right. So in this case, we're going to look at the infamous equation, E is equal to mc squared, or the famous equation. And also we're going to look at the decay law that talks a little bit about half-life. So for each section, you would expect around one question. So I'm going to ballpark between these two to be about 15 marks plus minus 2 marks. Okay. Look, Cambridge have to ask every topic, okay? Sometimes they realize that they run out of marks to ask. So there are years where they just ask you to sketch a quantum physics graph for 3 marks. Okay, lor. But some years they are like, oh, very deep dive into the experiment. So it's kind of like a gamble lah. You don't know which variant you will get. You also don't know how the questions will be selected. But it's almost like a 1-to-1 ratio, lor. If you know, probably you can answer. Right, so let's start with quantum physics first. Okay, so for quantum physics, the first experiment is the experiment that involves the photoelectric effect. So the photoelectric effect is basically the electron, or rather, not electron. This one is basically saying that light behaving like a particle. So it has a very particulate nature to begin with. Okay, so if you refer to the notes, sometimes they will ask you, this is not very important, but it's worth to memorize, that we are talking about, we're comparing the classical wave theory, so the wave that we have learned in AS, and then we want to compare it to the quantum theory. Okay, so if you're going to ask me to decide whether light is a wave or a particle, in 2023, we will say we don't know. What is the context? If I pass the light through a diffraction grating, then it will behave like a wave. If I, shine the light on a metal surface, releasing electron, that would be a particle. Okay, so which brings us to basically what the photoelectric emission is. Okay, so whenever you think about the photoelectric effect, try to, this one is again from my notes, so I'll just put this here as a diagram. Okay, so what we have is we have light carrying energy. So we know for a long time that when light is shined on the metal surface, the electron gets excited. So if you want to define photoelectric emission, is the release of an electron from the surface of a metal when light or electromagnetic radiation is incident on it. Okay, so there are two ways to look at the light. You can look at the light as continuous, which is the classical wave theory, or you can look at the light as discrete. Okay, but what exactly is continuous? The energy is continuous, but this energy is discrete. Okay, so quantum theory says that when light is incident, each electron will receive one wave packet. So this electron probably will receive this wave packet, etc., etc. This electron will receive this wave packet. So it's a bit like one wave packet per electron. Okay, it's like I think it's a bit like paying for school fees, right? You cannot share your fees with your friend, or maybe your results. Each student will get their own results. So this is what discrete means. Each electron will receive one wave packet or one energy, one quanta of energy. Okay, so the main focus here is that there are 4 observations that shows that this quantum theory work. Number 1, the ejected electron that we call photoelectron are ejected immediately. So you shine the light, it ejects immediately. It doesn't have to wait, because the energy of the wave is inside one packet, right? So once I take the energy, immediately I have enough, I can exit. But if wave is continuous, it's like boiling water. Even if the fire is very, very hot and you want to boil water, you have to wait. So number 1, the photoelectron is ejected immediately. Number 2, there is no photoelectron at all if the incident wave is below a minimum frequency. So this minimum frequency is known as your threshold frequency lah. So if I adjust the light, I realize if I drop below a certain F, I don't get any electron emitted at all. Okay. And number 3, what happens if I increase the F, the frequency? So changing the frequency of incident light or incident wave changes the kinetic energy of the photoelectron. Okay, so this means, right, from this section, I know that the energy of a photon is related to frequency and can be calculated using the equation E is equal to HF, or if let's say you want to use the speed of light, hc over lambda. Okay, where h is the Planck's constant, and c and lambda is basically the speed of light and the wavelength of light. So you can find the value of Planck's constant obviously in your data sheet, but I'll just include it here. 6.63 times 10 to the power of negative 34. Okay, and the c would be the speed of light. That's why c is equal to f lambda. All right, that's how they are related. So we still borrow the wave speed equation, but we're going to think about energy in a slightly different context now, okay? Which is only linked to frequency or wavelength. If I change the frequency, I'll change the wavelength, and both will affect energy. So from here, if it's not obvious to you, when frequency increase, energy increases. When wavelength decrease, frequency increase, energy increases. Okay. And finally, if you want to increase the rate of emission, only changing maybe I'll just talk about changing intensity. Changing intensity only affects the rate of emission of photoelectrons. So basically, what I'm trying to say is, if the intensity increase, there is more photoelectron per unit time. Rate of emission means more photoelectron emitted per unit time. Rate ma? Okay. All right. Changing intensity only affects this and doesn't affect the maximum KE, kinetic energy of the photoelectron. All right. So 4 observations. Sometimes they will ask you to list down 2 lah. Do you need to know all 4? Preferably yes, because sometimes we use these to evaluate situations. But it's pretty straightforward if you understand the model. Since each electron can only get 1 photon, if the packet is not big enough, the electron is like, meh, I cannot escape the metal surface. If the wave packet, the energy, the frequency is big enough, then the electron can happily escape. If I increase the frequency, I give the electron more energy, so the electron will have more kinetic energy. But if I increase the intensity, right, intensity only affects the number of photons. So think about intensity here is intensity increases, number of photons per unit time increase. It doesn't change the size of the photon, meaning frequency remain same unless you're told otherwise. So the energy of photon remains the same. So the main takeaway here is energy of photon only affected by frequency. If you don't change the frequency, you won't change the energy of the photon. Number 2, each electron can only have 1 photon. So even if you bomb the electron with a lot of photon, you make the light very, very intense, very, very bright. The light is like, the electron is like not enough. The frequency is not correct. Okay. And Einstein, by the way, who's the proponent for this quantum theory, which won him the Nobel Prize, has experimentally proven, if you're interested in the experiment, feel free to watch the recording, that the energy of the photon obeys the conservation of energy. Because once I provide the photon provides some energy to the electron, it will be the same as the energy used to escape the metal surface, plus whatever that is remaining, which is expressed as kinetic energy of the electron. Okay, but of course we expect a range because some electrons are deeper. So this one is a range of values. This one increases for electrons in deeper layers of the metal. They're deeper inside the metal and needs more energy to come out. And this kinetic energy will respond. So hence, this is also a range of values. Because this energy of photon is constant, especially if I keep the, only depends on frequency. So if I keep the frequency constant, there's only one wavelength or one value of F. Then the electrons from deeper inside the metal will have less energy left behind for Ke. So this means when I put it together in a min-max fashion, meaning if I try to take the most energetic electron, Ke max, so after I capture the electron that escaped the metal surface, I realize, wow, this electron got a lot of energy, the most energy. This means that it uses the minimum energy to escape. Okay. So if I can measure the fastest moving electron, then I can then also deduce that the energy required for that electron to escape is the minimum because it has the most energy after the event. But writing this in a more familiar equation, the minimum energy required to escape is known as work function plus Ke max. And the equation format, energy of a photon will be Hf, work function will be Hf naught. Ke max is Ke max. No, sometimes they just put E max. They will keep changing the symbol one lah. It shouldn't be the first time you realize this. All right, work function can sometimes be written with the symbol of flux, not to be confused with electromagnetic flux, but they borrow the same symbol phi. Just borrow and use only. Okay, not related. The second thing about Ke max, this is Ke max of an electron. Okay, so the change in Ke can sometimes be changed in electric Pe, especially if I want to link this to chapter 18, meaning I perform a photoelectric effect, I take the electron, and then I do another chapter 18 experiment or chapter 18 scenario. Okay, and finally, this one sometimes can be written as Hc over lambda. Okay, so these are the various format. I'm going to draw a box around this. Then we'll jump straight into doing some questions. So the photoelectric effect, the most important thing is you understand the 4 assumptions, and then based on that, be able to apply the equation and do some straightforward calculation. And also draw some graphs. All right, we will look at that. So for the topicals, we'll start with page 38. Let me print it out first. Okay, so as usual, we're going to do a variety of questions, starting with the one that has definitions in it. Okay, so for definition, all this, I mean, there's no better way to say it, but you are expected to memorize now. So let me expand the page a bit so that my hand will not look very weird and big. The photoelectric effect is the more popular or the more important experiment. So you will expect, generally speaking, more questions lah. All right. So for this one, you want to define the photoelectric effect. This is the emission of electrons. You can call it photoelectrons if you want to, from a metal surface when light is incident, or electromagnetic radiation is more accurate, but it's fine to write light. Okay. Right. Define work function energy. This is the minimum energy required in an incident photon for an electron to escape the metal surface. So it is the photon energy that provides the energy necessary for the electrons to yoink itself away from the metal surface. Okay, nice and easy. If I see simple definition like this and I understand the phenomena, they should be fairly straightforward to write. Okay, moving on. A polished calcium plate in a vacuum is investigated by illuminating the surface with light. All right. It is found that no photoelectric current is produced when the frequency of light is less than 6.93 times 10 to the power of 14. When you see the term no photoelectric current, that means there is no electron emitted from the metal surface. Okay. So name the frequency below which no photoelectric current is produced. This is called the threshold frequency. Use it for Cambridge A levels. You understand the idea of threshold, right? If let's say the grade threshold to get A for A levels is 190, you get 189. Sorry, no A for you. You sit for A levels again, and then you get 189 again. GG. Sorry, no A for you. But teacher, can I not combine my marks? I steal 1 mark from my previous session and put no, it doesn't work that way. You know it doesn't work that way. So yeah. So threshold frequency. Next part. Explain how the photon model of the electromagnetic radiation accounts for this phenomena. Okay, so we need to talk a little bit about what a photon is. So photon, discrete energy, right? So it's a discrete photons are discrete. Is the value is fixed packets of energy. So since the energy of photons only depend the frequency and each electron can only absorb one photon. Just like each student can only sit for one paper one time per exam season. So electrons do not have enough or sufficient energy to escape the metal surface. RIP. Okay. So the first mark here is when you mention, well, the photons are discrete lah, meaning they only have one value, which is dependent on frequency, 1 mark. And then the second mark is when you mention the energy only depends on, must say the word only, depends on frequency, 1 mark. Then the final mark will be each electron can only absorb one photon. So not enough energy. I can only take one, but if the one is never enough for me to escape the metal surface, it doesn't matter. You shoot 100 at me, there's no point. I can only take one. And I cannot combine the energy, so too bad. All right, part 3, calculate the work function energy in EV of calcium. So I want to point out how to convert electron volt. This term is called electron volt. It's just a different unit for energy. Okay, obviously this one is joule. So when we convert from EV to joule, we multiply by the electronic charge. When you go back in the opposite direction, you divide by electronic charge. Generally speaking, when it comes to EV, the numbers here are like between 1 to 10-ish for most of your calculation. 13, 14 also can. Okay, never mind. I scared now. Maybe I put 20-ish. So the numbers are more calculator friendly. That's why we provide a separate unit for energy, especially for the very small things like charged particles. Okay, so normally this is for particles. If you're talking about a ball rolling down the inclined plane, then nobody's going to use EV lah. They will use joule. All right. But regardless, to find the work function energy phi, I'm going to use HF because I have the value of F. So because these things are in SI unit, so 6.63 times 10 to the power negative 34, and the frequency is 6.93 times 10 to the power of 14. your answer will also be in SI units. So let me bring out my friend Casio. This will give you 4.59 times 10 power negative 19. This is in joule. So if you want to convert it to electron volt, you will divide by the electronic charge, 1.6 times 10 to the power of negative 19. Again, the value of E can be found from your data page. Coulomb. Right. So this means the negative 19 will go away now. So what I want is just 4.59 divided by 1.6. So that will give me 2.86, 2.87. So why did I write 3SF? Well, that's because if you look at the data given, this one is 3SF, right? You substitute this one as 3SF. So your final answer should also be 3SF. If you write 1SF, then you lose 1 mark, that will be very sad. All right, so the mark would be here if you know the equation and can substitute the right things inside. The second mark is the conversion, so writing the final answer in 3SF. Okay, for a total of 9 marks. Very nice. I like questions like this. Easy, straightforward, asking basic definition. But we're going to move on to level up a bit. So let's look at page 41. Okay. So 41, I'm presented with a graph. I won't panic first. I will define what is a photon. We defined it just now already. It's a discrete packet of energy electromagnetic radiation. And I'll give them the equation also. I don't think in the recent years the equation is necessary. I always write the equation. In case, I mean, just to show how discrete it is. It just depends on F. So the 2 marks here, 1 mark would be for the fact that you know it's a discrete packet of energy. This one can also be called quantum. Okay. And then you mentioned that this is electromagnetic radiation. One word. Okay. So the EM radiation with changing frequency and constant intensity is used to illuminate the metal surface. At certain frequencies, electrons are emitted from the surface of the metal. And this is the KE max, maximum kinetic energy, to frequency. So I'll name this phenomena. This is photoelectric effect. Very nice. Moving on. Describe 3 conclusions that can be drawn from the graph. Conclusions may be qualitative or quantitative. Wow, let you freely express yourself. Okay, I want to remind you whenever you see a list here, it should only have one statement beside each number. So you cannot be like, oh, well, wave energy is discrete and there is threshold frequency and the frequency only affects KE. That is 3 point already. I mark 3 point. I won't read these 2. Does that make sense? So make sure each point is distinct, and number two, they don't contradict each other. Okay, so the first conclusion that I can draw, because the graph looks like this, right? So this means below this value of f, because this graph here is f, below this value of f, there is nothing, meaning there is no electron. So you could say there is, or there exists a frequency below which no electrons are emitted. They say it can be qualitative or quantitative. So I will write the qualitative in blue, and I'm going to write the quantitative in green, but they are the same point, okay? So you could say that the minimum frequency for electron emission is 5.4 times 10 to the power of 14 hertz. This value here lah. You write one of it enough already, okay? What if the blue one is correct, the green one is wrong? Then why you want to give yourself that pain? Depends on the recommendation given by Cambridge, which changes from year to year. So my best advice here is write one, whichever you are more confident with. Okay, next one. Since we talk about the x-intercept, there's no y-intercept that we can see, so maybe we can think about the gradient. Because whenever I want to describe a graph, when I see graph, I think about, x-intercept, y-intercept. This is level 1. Level 2, gradient. So maybe I can figure out what does the gradient represent. Okay, so I think I'll go back here to stare at the axis for a bit. I have Emax on the y-axis. I have frequency on the x-axis. So I'm going to write the equation here. Energy of photon is equal to work function plus Emax. Okay. So right now, Emax is my y-axis. So I'm going to rearrange to make Emax the subject of my equation. This will mean that Emax will be equal to energy of photon minus the work function. Okay, but I want to find out what's the gradient of the graph, meaning I need to find a way to bring frequency inside. But never fear, energy of the photon is HF minus work function. So if I compare with the general equation of a straight line, y is equal to mx plus c, you see your gradient is your Planck constant. Of course, if you are familiar with this topic, you will immediately be able to tell this is the Planck constant. But if not, I don't think these few steps are too difficult to do. Always start with the concept or the law or the idea, conservation of energy, and then open up from there. Okay, so I could just say the gradient is the Planck's constant. Do I need to calculate? No, don't need. Qualitative ma, right? So I can say that the gradient of the line is the Planck's constant. Planck. I don't know how to pronounce his name. I guess since it's a name, better I make sure the P is big. Slight spelling error for physics is okay, but try not to lah. You can always go back to your question paper and copy his name. Table of data, copy the name in. Okay, so there's a Planck constant H. If you want to write the qualitative value, then you could say, the quantitative, you can say gradient of the line is 6.67 times 10 to the power negative 34 joule second. Okay, so we looked at x-intercept, y-intercept, gradient. The next thing we're going to look at is probably something to do with the trend. So from here, you can see as F increase, KE increase, or rather the Emax increase. Because the graph here is Emax and here is KE, I mean frequency, right? So I could say that the Emax, maximum KE, increases linearly with increasing frequency. This one got no quantitative option besides maybe writing the equation, but I don't want to lah. Okay. So whenever you are asked to use a graph, I don't care which chapter, okay? Think about whether the x-intercept, the y-intercept, or basically important coordinates. Think about the important coordinates. Does the coordinates represent anything? We cannot talk about y-intercept, not because you cannot find it, but because the graph is not on the graph, it's not present on the graph. Okay, the coordinates, right? Then after that, you look at the gradient, nothing else to say for this. And then finally, you look at the trend. If it's not linear, then you could just say increase. When frequency increases, kinetic energy increases. Cool. So 1 mark each, please don't contradict yourself. Part C, experiment B is repeated twice, each time making one change. Okay, state with a reason how the graph will change when a different metal is used. Well, different metal means different work function, because work function is the energy required to yoink the electron or to allow the electron to escape. How the electron is bonded inside the metal surface depends on the type of metal. So different metal, different work function, different threshold frequency. Threshold frequency F naught. Okay. So that means I expect, I'm going to draw the original graph here. This is the graph looking like this. This was my threshold frequency, F naught. So the F naught will change or either move forward or move backward. So I'll mention this. So different metal, different threshold frequency. They didn't say whether the threshold frequency increase or decrease, so I don't know. It could be either direction. Okay. But the gradient of the line, since it's the Planck constant, remains the same. So something like this could also be something like this. Depends on whether the work function threshold frequency decrease or this side threshold frequency increase. No information, so you just say different metal, different threshold frequency, and the gradient remain the same. Remain the same. If different threshold frequency, right, then different intercept on the f-axis or the horizontal axis. Okay, same metal is used, so same threshold frequency. Electromagnetic radiation intensity is 2I. Remember, intensity doesn't affect your KE max. So for this one, although the intensity is double, photon energy only depends on frequency. And because of this, photon energy remains the same, doesn't change. So the line remains the same. Because if you think about it, I have energy of photon, which didn't change. is equal to work function, which didn't change because same metal, plus Ke max. If this one doesn't change, this one doesn't change, this one also wouldn't change. Okay. So I will level up and give you part 3. Same metal, same intensity, but frequency 2F are double. So if your frequency is double, right, it just means that your graph is longer. That this so from here, let's say this is F1. Then I double it, then here is 2F1. The line is, this is a troll question. The line remains the same gradient and intercept on the f-axis. Just that the range of values is doubled, meaning you have more data. Only the range of f increases. Or in mathematics talk, your domain increase. But it's still the same line. Okay? So if you understand the concept, they can change it, however, but you are like, okay, no, you change, then I respond accordingly. So that, in a nutshell, is the photoelectric effect. I would suggest you try, if you want to do more this type of question. The recent years, you can try ON22 P41 question 8. This is about the changing the photons, either frequency or intensity. Why is my handwriting so today? ON22 P41. Okay, and then there is one that I don't want to do for you because I want you to do first. So if you don't know, or you haven't tried this question yet, May June 22 P41, question 5B. This is the paper variant where I think they set the whole paper and then go like, ah yeah, I've forgotten to set a quantum physics paper question. Then they ta-da. Okay, so try this. This one is about graph sketching. And I will rate this a 2-star difficulty lah, meaning some people will have some struggle. The rest are fairly factual, so it should be fine. So that's the photoelectric effect in a nutshell. Okay, so try these two. All right. So the next thing we're going to look at is the second experiment, which conveniently they recently just asked, so I can discuss that. The second experiment is the electron diffraction. So case number 2. So the electron diffraction is basically saying that now electron behave like wave. So this is the wave-particle duality. Electron like wave, wave like particle. Everything is a blur. Correct lah. Welcome to quantum physics. Okay, so for electron diffraction, the equation that we're going to use is the de Broglie equation. Momentum of an electron P is equal to Planck constant divided by lambda. This equation very tricky one. Because on one side, you have momentum, which is a particle nature. Right? You need to have mass, they only have momentum one. Okay? Then you have wavelength, which is obviously a wave property. I don't look at you and go like, oh, your wavelength is 3 meters, right? Because I'm like, what does that even mean? I am not a wave. But when things are really, really small, they begin to behave like wave. Of course, then here is where science fiction begin to open. Science fiction be like, hey, wait a minute, if the very small particle can behave like wave, but we are made out of very, very small particles. Maybe if we can break ourselves apart into small particles, then we can diffract. Okay, that one a bit science fiction, but maybe, who knows, in the future. H is our good old Planck's constant. Okay, so I guess it's worth writing down a few more related equation. Momentum P can be calculated using mass times velocity, right? But if you want to calculate the value of V, sometimes when we accelerate an electron, so let's say I have an electron between two parallel plates, this negative plate, this positive plate, and the electron here, I want it to accelerate with a velocity v. Then maybe after it escaped this metal plate, I put it through a diffraction, whichever. Okay, so let's say the electron here has U. I mentioned to you before just now in photoelectric effect, but the change in kinetic of energy of the electron is the same as the change in electric PE. So to find electric PE, you're actually going to use the equation EV, where V is the potential difference between the plate. This is your chapter 18. Okay, so here will be half mv squared minus half mu squared. Of course, if your U is 0, if your electron is stationary, then it's just half mv squared equal to EV lah. Just in case, chapter 18 stuff here. Okay, so we're going to look at the electron diffraction now. Just want to point this out to you. I'm going to refer this to page. Let's do some calculation first. So let's do page 39. Okay. So state an experimental phenomena that provides evidence for the particle nature of electromagnetic radiation. This is the photoelectric effect. And then the wave nature of metal. This will be the electron diffraction. Easy mark. A particle of matter move with a momentum p. State an equation that gives the wavelength of the particle. Name the other symbols used. Okay. P is equal to h over lambda. I use P, I use lambda. You say h is Planck's constant. Is it a bonus? I think it's a pandemic bonus. I don't know. Okay, the name given by the wavelength. This is called the de Broglie wavelength. Okay. So electrons are accelerated from rest. So very good. The initial kinetic energy is 0 through a potential difference of 4.8 kilovolt. So imagine this is a parallel plate. Again, this is negative, this is positive. My electrons was at rest here, and eventually it will travel with speed v. The potential difference from here to here is 4800. Okay, so what we're working with is the change in kinetic energy is the change in electric P. Normally in your A2, if you're able to recall a concept, whether it's conservation of energy or some law or some main idea, it's good to start from there, okay? Because that will guide your working. Here you can write half mv squared minus 0 because it was at rest. And the electric PE will be E or Q delta V. This was how it looks like in chapter 18. But the charge is E, right? And the change in potential is 4800. Okay, this will be half mv squared. So if I want to find v squared, it will be 2e times 4800 divided by m, where m is the mass of the electron. So I can substitute now. 1.6 times 10 to the power of negative 19, 4800 divided by 9.11 times 10 to the power of negative 31. If you do too many questions like me, you will remember the constants. You don't need to remember, you can always refer to the front page, okay? The purpose of physics is not for you to memorize constants. It's for you to be able to solve questions and describe phenomena and understand how it affects where we are right now in our understanding of the world. Okay, don't forget to square root. By the way, if I forget to square root, then my electron is traveling faster than the speed of light, and that frankly freaks me out a bit. 4.1 times 10 to the power 6. Prove it. Okay, so if I see some conservation of energy, especially the equation, this part here, you get 1 mark. Then you substitute everything correctly in here, then you get the second mark. Okay, next, calculate the effective wavelength. Just use the equation now. P is h over lambda, but mv is h over lambda. I want to look for lambda anyway, so I'll just rearrange h over mv. So 6.63 times 10 to the power of negative 34 divided by 9.11 times 10 to the power of negative 31 speed. Even if you can't prove, you could use the speed. 4.1 times 10 to the power 6. Okay, this one is, check. Okay, so 1.78 times 10 power negative 10. They did put 2 SF lah, so if you want to, you can write in 2 SF. So normally for de Broglie wavelengths or wavelength involving the quantum physics, you expect very, very small. Okay, like less than 1 nanometer. If you get something really big, that's just very weird. All right, so this kind of question is nice because it's just knowing the equation and just doing pretty straightforward substitution. Make sure you give yourself time to clearly show the substitution. Okay. Wait, did I? 7:30. I pressed wrong. Ah, so I stand on 6, 7, 7 here. This is negative 11. Why did I put 6 up there? This one. Ah, yes, it's 4.1 times 10 power 7. Okay, my bad. Okay, so this is the more straightforward one. It allows us to see the scope of the question. We're going to move on to a more recent one from Feb March 22. So this question, they show us the electron diffraction observation. Okay, if you look at your notes, I got put color picture lah. But generally, we will accelerate the electron through a potential difference. So the electron will have a certain speed v. This is the electron. Okay, and then we shoot it through a thin layer of crystal. This is the thin crystal. Okay, and then we incident on a fluorescent screen. So on the screen, if you open up the screen, you'll be able to see this kind of concentric rings. Okay, on the screen lah. Side view, then you see just the bright dots. Okay, so this is what is observed on the fluorescent screen. Okay, I think I want to get the easy mark part A first. Formula for de Broglie wavelength. I guess I could rearrange h over p. You tell us more. H is Planck's constant. It's only in the modern physics where they will ask you easy questions like this. So take it. It's the momentum of the moving particle. Okay. So name the phenomenon shown by the electron at the crystal. This is the electron diffraction. State what this phenomenon shows about the nature of electrons. Electrons have wave properties. Okay. Part 3. Suggest why your thin crystal can cause the phenomena in B1. The reason why thin crystal is like that is because if I zoom in the crystal, right, the atoms are very, very close together. So this one behaves like a diffraction grating. There's a gap between the particles. And that gap between the particles is the one that causes the electron to diffract. So the electron passes through the gap and then it shows diffraction pattern. Bit weird lah, but in the world of quantum, we only describe what we know. Okay, so I can say that the space between the atoms of the crystal is approximately the wavelength of the electron. So this means the gap size is more or less equal to lambda. Diffraction occurs. Okay, moving on. The electron is accelerated through a different potential. Now we have a new pattern. It looks like the rings are closer, tighter. No? Okay. State and explain the changes that have been made to the potential difference to create the pattern shown in figure 8.2. So let me pull up this picture and point out the bright dots at the corner. Okay. So the rings, right, actually depends on this angle theta. So if the rings are closer together, this means my theta decrease, right? The theta decrease in d sine theta is equal to n lambda. So I know this is an AS equation, but you see diffraction is still this equation. Okay. So if my theta decreases, assuming my crystal is the same crystal, this is your gap size D, okay? And the number or order here will be, this is n equal 1, n equal 2, n equal 3, so n is the same. So if theta decrease, this means lambda decrease. Okay, so I'll write down that. I would say the electrons diffract less. So because of this, wavelength of the electron decreases or decreased because this is what we see. So what can cause the wavelength to decrease? Now I need to bring in my new formula. Lambda is equal to h over p. So if I want lambda to decrease, I need my momentum to increase. So momentum of the electron increased. So if I want the momentum to increase, because momentum is equal to mv, so for momentum to increase, the velocity will have to increase more, which means the accelerating potential difference will increase. So hence, for the electron to have greater speed so that it has greater momentum, the accelerating potential difference is increased. Okay. So this kind of question is, they can only ask like that now. All right, they draw a different pattern for you. So just know that when the wavelength is smaller, it doesn't spread out that much. So if I want the wavelength to be smaller, I need the momentum to be bigger. For the momentum to be bigger, then your accelerating potential difference should drop. Should increase, so that the electrons have a greater speed. Okay. I think the last one I want to do before we take a break is the one where I see people ask a lot in the forums, but then it's quite straightforward lah. So look at FM22. The FM22, no, it's actually before that. Winter 21. Just look at A and B. And then you can see this one happening all over again. So I'm going to skip A, okay? It's the same thing. Particular nature of this is photoelectric experiment. Wave nature of matter would be the electron diffraction. All right, calculate the de Broglie wavelength. This one, we did many times now. So use this lah, okay? I just want to point out that your mass is 4U. Okay, the U is your atomic mass, 1.66 times 10 to the power negative 27. Wow, 3 marks are not bad. Okay, then you substitute. 6.63 times 10 to the power negative 34. Hopefully you will not write this as messy as I am writing it now. Times 10 to the power negative 27. And then V would be 6.2 times 10 to the power of 7. Okay. Very nice one, the calculation for quantum physics, because there's only that 2 equation. It cannot trip you up. All right. So I'm thinking if you write the equation, including MV, you get 1 mark. If you know that the mass is 4U, you get another mark, and your final answer is the last mark. Okay, so I'm going to press it in my physical calculator because it's faster. So this wavelength is going to be really short because alpha is a lot more bigger than the electron. Okay, this is so short, man. Okay, anyway, the speed of the alpha particle is gradually reduced to 0. Okay, sketch the variation of V to lambda. Lambda is H over mv. So it looks like it's inversely proportional, right? And the lambda is very, very short here. So it's probably going to look like this. Of course, we have the whole asymptote situation going on. So let's draw something like that. Can't already, it's a sketch. Shape is 1 mark. So meaning it as V decreases, lambda increases. You get the lambda is inversely proportional to 1 over V shape. Okay, and then the other mark is treating this like an asymptote. So let me try to draw it so that it looks like an asymptote. So I should try to make sure that by the time I reach 6.2, it's not yet a plateau lah. Try. But the other axis should look like a plateau. Bit hard to draw on the tablet. Something like this. Ish. Meaning asymptote. Here is very small already lah. This side here also asymptote. I think that's the second one. Okay, finally, suggest an explanation why people are not observed to diffract when they walk through a doorway. 1 mark, 3 lines. Okay, so if you look at the calculation for the wavelength that you, for alpha, right? This is already very, very small. And a doorway, I don't know what door you are talking about, but there's no way a doorway can be this small lah. Okay, so you can say that the wavelength of people are much smaller than the gap size of a doorway. It's not going to happen. It'd be cool though, don't you think? It would be very cool. Okay, make sure you mention not just smaller, much smaller, very, very much smaller. All right, so we're going to take a break now. It's around past the 1 hour mark. We'll come back after 10 minutes. And then today's class will probably extend to a bit late so that I can wrap up 2 chapters for you, seeing that your paper 4 is coming soon. Are you okay? All right, I'll see you in 10 minutes. And then I'll check the chat. Okay, the third experiment in quantum physics is they call it the hydrogen line spectrum. Because once we understand that electrons behave like wave, the easiest way for us to study that behavior, one of the phenomena, is to look at the hydrogen line. So in the older past year questions, they have asked us to describe why sometimes we see dark lines on continuous spectrums and why sometimes we see colored lines. Okay, so that one I will leave it to you in your notes. The only thing I want to point out is this one is oftentimes nowadays we can combine this with chapter 25, astrophysics. And the reason why we can combine this with astrophysics is because the hydrogen line spectrum allows us to observe the Doppler redshift. Okay, so I don't think I'll spend too much time here because we'll probably encounter it again very near in your future. But I just want to say that whenever there is a electron, let's say this is the line transfer. Okay, so whenever you have an electron, it can transfer, absorb energy to transfer up. This energy is in the form of photon. Okay, so it can transition up. Let's say it transition from E1 to E3. Okay, so in this process, I can say that the energy of photon is equal to E3 minus E1. Okay, so all the energy levels can be changed to HF3 minus HF1. Then this is the energy of the photon, HF. It can also be Hc over lambda 3 minus Hc over lambda 1. And this one is your Hc over lambda. Okay, so the calculation for this is fairly straightforward. You can refer to your notes. So we are going to now move on to chapter 23. Okay, so this one all, because I look at the recent past years, right, they have started to combine this with chapter 25, which is what I would have done also, because it's the electro. It's a nice way to ask two things, kill two birds with one stone, ask two things in one question. Okay, so the last time this one came out as a standalone, I think was summer 20 P41. So it's been a while lah. Okay, take as you may. Go try some questions if you need to. Okay, they are recorded in the channel as the main examples already. Okay, and another one I want you to also think of trying besides that, under this is the ON20 P41 question 11. This one is the electron colliding with a photon. They call it the electron deflection. Not diffraction, but deflection. Okay, deflect. All right, go try this too. Okay, we can now move on. 23. Nuclear physics. So for nuclear physics, it's the thing that is new is not the equation E equal to mc squared, but more of the idea of binding energy. So the first one we're going to look at is the energy stored in the nucleus, aka binding energy. And we defined binding energy. I'm going to use BE as a short form. So BE is defined as the energy required to separate completely to infinity all the constituents, basically all the protons and all the neutrons in a nucleus. You could also say all the protons and electrons, if constituents feels like a strange word to you. All right. So like all equation, whenever there is a calculation here, binding energy can be calculated using the equation delta mc squared. Okay. So I think this one is probably no big deal. Go try out some questions if you need to. Just remember, if they give you 10 SF, please use all the 10 SF, okay? Don't try to skimp on the SF. All of them are needed. Okay. So from here, the last thing I want to talk to you about is the graph about binding energy versus nucleon number. So this one is the number of nucleon. Right. So the graph tends to look like this. Okay. It will peak at 56. Sometimes they will ask you to sketch this. Just know that 56 or iron, Fe, is the most stable nucleus. That's why the Earth's crust or the Earth's core is made out of iron. Okay, so everything wants to be iron. If you're too small, you will fusion together to become bigger so that you're closer to iron. If you are too big, you will fission, you will break apart. Okay, so I think this one, no big deal. try some questions. They're not really that popular anymore, but the same thing apply lah. Know how to use the equation, know how to write a balanced chemical equation, right? So the main focus of this topic that is new, at least new to your understanding, is the decay law. Okay, you have seen the decay law before in this format. So you have looked at the half-life. So maybe let's say I have the number of radioactive particles in a sample. Okay, so let's say I start with N naught. So you know already if it becomes N naught over 2, this is half-life. Then if it becomes N naught over 4, this is 2 half-life. And we can keep dividing by 2. So this is your first introduction of half-life, okay? Meaning the decay law tells us that we can keep dividing by 2, and the time interval to the next division of 2 will always be the same, all right? So then we stop there, lor. But now, after your IGCSE or your SPM, we'll move on a bit and we'll try to define what decay law is by first telling you that for us to use the decay law, we are making 2 assumptions, that the reactions are random and spontaneous. Okay, so we are assuming that all the chemical reaction is random and spontaneous, right? Sometimes they will ask you to define what these things are, which is okay. These are things that I memorized before the exam. Okay, so it's important to, I guess, write it down somewhere. But yeah. So random means you cannot tell which particle will decay first. So let me show you where to find it in the notes. You will find it somewhere here. Okay. So random tells me that I cannot predict which nucleus will decay next. All right, so if you look here, cannot tell the time at which the nucleus will decay. Maybe I can full screen this. There we go. Okay, so always refer to your notes for the more accurate definition. Okay, cannot tell which nucleus in the sample will decay next. Cannot tell when it will decay. Just random lah. I feel like it. I feel like doing it. It's me. I am the nucleus that's going to decay. Don't know. So basically, there's a constant probability that a nucleus will decay in a fixed period of time. Okay. Number 2 is spontaneous, meaning it's not affected by external factors such as temperature or pressure. Okay, we cannot make it happen by changing the temperature or adding a catalyst. Okay, so that is random and spontaneous. So once you know that they are random and spontaneous, then decay law says that the rate of decay, dN dt, is proportional to n. Okay, so if they ask you to define the decay law, this is the definition. But in some mathematics that is not really important for physics, it's important for me as a person now, but it's not really important for physics. When we solve this equation, we get n is equal to n naught e negative lambda t. So the solution for all of the equation that starts with this format or this law will always look like this. If you're interested in the decay law derivation, it's also recorded as a bonus video. But today we're just going to practice using this. Okay, so this n is the number of radioactive or not yet decayed nucleus in the sample. N naught is the initial sample, initial number of nucleus in the sample. Okay, when I say number of undecayed nucleus in the sample, I mean at time t. So this is the time. 1 second, 2 seconds, 2 hours, 200 years, depending on the sample we're talking about. But the more important thing here is my lambda. Okay, lambda is known as the decay constant. Okay, and if you want to know its definition or why is it derived that way. We'll have to refer to the derivation, but we can also sort of memorize it. Lambda, right, is basically the substitution of the proportional sign. I mean, there's a negative here to show that the value decreases. So this lambda is actually dn over n. If I bring this n over to divide. So this one would be the dn over n is the probability. So the probability of decay of a nucleus per unit time. Okay. And then from here, we are going to define activity A as dn over dt. But if you learn maths, you will know that whenever I differentiate the exponential function, I will get the exponential function again, meaning my equation will now look like A is equal to A naught E negative lambda t. Okay, so where A is the activity at time t and A naught is the initial activity. Okay, so activity is a new physical quantity. The unit here is Becquerel or BQ. And if you want to link them together, the link between these two that is convenient to use is A is equal to lambda n, because I let this dn dt be equal to A, right? Dn dt becomes equal to A. So A is equal to lambda n. Okay. So since lambda is such an important equation, we should be able to determine lambda like how we determine the time constant in discharging of a capacitor, right? So to determine lambda, well, let me check your new equation list. Old equation, they got give. New one got give. Okay, great. So in the formula list, you will be given these two equations. So if you observe, in place of x and x naught, I can put n or a lah, depending whether I want activity or the number of decayed nucleus. Okay. And then to find lambda is 0.693 over half-life, or my preference is ln 2 over half-life. Okay. So I'm going to segue a bit to remind you how to derive this relationship, because occasionally you will be asked. Okay, so to find the equation of half-life, I'm going to start first by using either n or a, e negative lambda t. And from the definition of half-life, when t is equal to half-life, n is n naught over 2. This is the definition of half-life. Half-life. Time taken for the number of radioactive nuclei to decrease to 50% or half. So I'll substitute that in, and I will substitute as n naught over 2. So on one side, I have n naught over 2. This is n naught e negative lambda t half. N naught and n naught will cancel. So on one side, I have half e negative lambda t half. E bring over ln half, negative lambda t half. Ln half is negative ln 2. So negative will obviously cancel. Finally, I will have lambda is equal to ln 2 over t half. So we're just substituting t as half-life and n as n naught over 2. So pretty straightforward equation. Okay. So the question people are asking me, let me see, is winter 22. Okay, so let's do that. Okay, so in a nutshell, what you need to know about decay law is all here lah. This equation, you also have to know how to linearize them. Okay, and then finally being able to prove that lambda, right here, lambda is ln 2 over half-life, or 0.693 over half-life. Okay, next. In the topicals, this will be page 42. Let me zoom out. Okay. So here's an example of them asking you the basic assumptions. Here it says that carbon 15 is an isotope of carbon that undergoes radioactive decay to nitrogen 15, which is a stable isotope of nitrogen. Okay. So if you want to, you can write the equation, but since they never asked, I am not going to write lah until it's required of me. All right, so here it says that say what is meant by random. Random means you cannot predict. So we cannot predict which nucleus will decay next, or when a nucleus will decay next. All right, spontaneous. The rate of decay is not affected by external environment. Environmental factors. Okay. After that, I see a graph. Okay. So here it says mass of the carbon of the sample decreases over time. So this is ln m. And then the first part here, they're asking you to demonstrate that the radioactive decay is random. The zigzag fluctuation line. Okay, so I can say that although there's a trend, that is trending downwards, the line fluctuates. So it's the fluctuation that shows the random property. Sometimes don't know why suddenly got a lot decay, so there's a maximum point here. Sometimes don't know why suddenly the number of decay decrease, there's a minimum point here. So next you're asked to draw a line of best fit. Okay. So I'm gonna try my best. But the idea of line of best fit is you want the points, or rather you want the line to pass through evenly across and balance all the fluctuation, you know, something like this. Here is, let me adjust. It's a bit hard to draw without a ruler lah, on the paper. So basically what you want is you want the amount of black color underneath the red line to be the same as the amount of red color, the black color above the line. Something like this. Okay lah, good enough. Ish. Okay. So there's a little bit on top, but there's also significantly a lot below. They balance out. The points above the line is more or less the same amount as the points below the line. Okay, 1 mark only. Moving on. Show that the decay constant is given by the magnitude of the gradient of your line in B2. Okay, so if you are doing physics at this level, we expect students to be able to basically understand the relationship between mass and the number of nucleus. Okay, so this one is mass, right? Mass of carbon 15. So we have this equation. But how do I find the number of particles? I take the mass multiply by the Avogadro constant, right? Because the number of particles would be, how should I define it? The number of moles is equal to the, let me brain a bit first, because I don't want to go to blunder and come back. Okay, but I guess I have to. Number of moles would be the mass divided by the molar mass. Right? This is the number of moles. But the number of particles is the number of moles multiplied by the Avogadro constant. So the number of particles is the number of moles multiplied by, or rather the mass divided by this molar mass or relative molar mass. Can I just, what symbol should I call this? I call this MR. Okay, times the Avogadro constant. Okay, so number one, number of moles, N. N is the mass of the sample divided by molar mass. Molar mass here is basically the number lah. In this case, the molar mass is carbon 15. So if you want to, you can even write this one as M divided by 15. In gram, divide by 15 gram. So the gram and gram cancel. Okay. To find the number of particles, I will take the molar mass, the mass divided by the molar mass, number of moles, multiply by the Avogadro constant. Because 1 mole is 1 Avogadro, 2 mole is 2 Avogadro. But I don't really care about any of this, to be honest, because all I want to show here is N is equal to, this 2 is constant, right? So if this 2 is constant, then N is equal to K. Any constant, I'll just put K. And you can put whatever alphabet you want. Which means on one side, I can put Km. On the other side, I can also put K, initial mass, M naught. Initial mass of the sample, and E negative lambda T. So the K and K can cancel. Like whatever you do on one side to find the number of particles, you will repeat the same thing on the other side to find the number of particles, and they cancel out because all I care about is the mass that is remaining and the mass that we started off with. So it depends on, I guess, your ability or your dexterity to understand that when it comes to this decay equation, in front here can be a lot of things one. As long as you can show to yourself, and the same thing also applies for your electromagnetic effect or your Faraday and your Lenz law. If things are directly proportional and it exists in a differential form, the faster you can tell that they are interchangeable in your mind, the better it is. But before you adapt to the ability to translate across variables, then justify it for yourself. Number one, write down what you're trying to substitute N with, which is mass. Okay, so then I need to think about how do I include mass inside the calculation to find the number of particles. So I find the number of moles first of all, mass of sample divided by molar mass. I don't care to substitute lah. Okay. Number two, I find the number of particles. So number of particles, N, is the number of moles times the Avogadro constant. But the number of moles is also the mass of my sample divided by the molar mass. And this molar mass and the Avogadro constant are constant, right? So I just put them together, constant K. I guess if you want to, you could write that K is equal to NA over the molar mass, MR. It doesn't matter because they exist on both sides. We can cancel them out. Okay, so your mark only start when you are able to reliably, basically when you are able to write down the equation instead of n is equal to n naught, now it's m is equal to m naught e negative lambda t. Okay, so from here, the graph that I'm plotting on one side is ln m. So I ln both sides. Ln m is ln m naught. Multiply means plus ln e negative lambda t. So if I rearrange, this is ln m, this is ln. I mean, ln e is 1. Let me rearrange first. Negative lambda t plus ln m naught. So this one is 1. Ln to the power e is 1. I can bring down lambda t. Ln e plus ln m naught. Do as many or as little steps as you need. Okay, negative lambda t plus ln m naught. So once you reach this equation, y is equal to mx plus c. So hence, gradient is equal to negative lambda. We are looking for students to reach this form. You reach this line, that is the mark. How many steps it takes depends on your ability to do logarithms. Okay, so use the line to determine lambda, give a unit to your answer. So to find lambda, I need to find the gradient, right? Look for the gradient. Okay, so you might be asking me, teacher, what about the issue of units? Well, you look at the equation. In this case, right, what's the unit for ln m? Ln m has no unit. Ln itself is unitless. You freeze the unit inside the bracket. For more information, you can look at the 3 video lecture series of me talking about ln and how to ln and why we ln. But the short answer would be the grammar is inside this thing. You see a bracket? It's not the unit. There is no unit. Ln is essentially unitless. Even if there is a unit, it's frozen inside the ln. Watch the recording to see more examples. Okay, so ln m, unitless. It is this 10 to the negative what? 10 to the negative 16 gram is frozen inside the ln. I use the word frozen, but it's basically, it's not there, it's inside. Haven't used yet. When you want to use, when you anti-lock. Okay, so for example, let's say I read ln m is equal to, let me take this number, negative 5 or 5.2. Let's take this one. Maybe I'll need to use it later. So let's say I take this number, which is negative 4.8. So ln m is negative 4.8. Okay. By the way, I'm not answering. I haven't answered the question yet. Okay. I'm just telling you what to do with the unit. So ln m is negative 4.8. Okay. This m was ln m times 10 to the power negative 16 gram. Okay. So in order to find m, you will take e to the power of negative 4.8. So you bring the log over to become exponent. Okay. And then you times 10 to the power of negative 16 gram. So only when you anti-log, the unit gets unfrozen. And now you can press calculator if you want to. What is this? Negative 4.8. So now your m will be 8.22 or 8.23. negative 60 times 10 to the power of negative 19. Okay. So ln itself has no unit one. The unit only unfreeze itself when you anti-lock, when you anti-ln, when you kick the ln over. Okay, so no unit. Likewise, this one also unitless. Meaning lambda and t should also be unitless, right? So the unit for lambda will be the unit for 1 over t. So the unit for lambda will be equal to, because unitless is 1, right? Second negative 1. Check your understanding of half-life here. To find lambda, I take ln 2 over half-life, right? So isn't the unit second negative 1 because half-life is underneath? Another way to check is look here at the, what's it again? This one. They mention here half-life. Okay. Also per unit time. So the unit for lambda is second negative 1. Okay. So this many different ways tells you how to handle the log. Let me know if you have any follow-up questions while I find the gradient for you. If don't have also, please let me know so I can move on. Anyway, I'm going to take this point. Negative 4.80. This is a nice point. Let's take this one. This is 0. Negative 4.8. This one would be 8. Negative 7. So the gradient would be negative 7, negative 4.8, 8 minus 0. Am I bringing it correct? So this would be negative 0.275. If you want to include the unit, ln m has no unit. So up here is unitless. And down here, the unit is second. That's why it's second minus 1. I would include more SF in my writing. So hang on. This one would be negative 7.0 minus negative 4.8 divided by 8.0 minus 0.0 . You can keep your answer into 2SF if you want to, which is what I prefer. Okay, next, use your answer to calculate the half-life of carbon-15. Well, T half would be ln 2, lambda over ln 2 over lambda. Because lambda is ln 2 over half-life, or 0.693 over half-life. You can copy from the picture, I mean from the formula page if you want to. So ln 2 divided by 0.28. Wait, should I leave a negative? Oh no, gradient is negative lambda. So this one is positive. Because time cannot be negative, right? Anyway, there'll be ln 2 divided by 0.28. This is 2.48 seconds. Even if you don't know this unit, you can use this to help you. Okay. So hopefully that's clear about how to handle unit. Ln has no unit. If there's a unit frozen inside, then unlock. It only comes out when you anti-lock it or anti-ln it, or you bring the ln over to become exponents. Okay. In the paper 5 lecture series, I recorded a deep dive into how to handle log and ln in your paper 5. Make sure you know what to do. Okay. Part C, the equation for decay of carbon-15 can be written as this. State and explain how the mass of the product of decay must compare with the mass of the carbon-15 nucleus. So during this reaction, surely will release some energy one. So this energy is the delta mc square, meaning the change in mass over c square. Okay, so I would say energy is released. All decay that goes towards stability, energy will be released. Okay, during decay. Let's say this energy is from the decrease in mass, delta M. Hence, the total mass of the product must be less than the reactant carbon-15. Reactant is a chemistry person phrase. Okay, so I want you to understand that all spontaneous decay, fission or fusion, releases energy. So we expect the mass to drop one. All spontaneous decay. If it's not spontaneous, if it's a decay that you make happen, then that's a different story. But most decay that we study, if not all, in this topic is spontaneous because we're studying nuclear decay, not chemical reactions. Although nuclear decay is a type of chemical reaction. Okay, so this is the question that is requested. Hopefully that makes sense. Wilin, okay or not? Let's see if we can. Right, that's great. Let's see if we can find another one to do. Okay. In the similar vein, we can look at page 37, which is winter 21. We'll do one more before I talk about the electromagnetic induction question. So nuclear decay is a very nice one. The questions are all, again, very predictable. As long as you do enough, by enough I mean at least 3 to 5 years, then you should be okay. All right, this one, random and spontaneous, I'm going to skip, okay. Here we have a sample, and now today they put activity. Great, I guess. The time is in minute, sure. And use figure 12.1 to determine the half-life in minutes of nuclide X. So this one is actually harder because they don't like guide you step by step. Find the gradient. Show that the gradient is lambda, then find the half-life. This one is all in one. Okay, so if you remember that lambda is equal to negative gradient of the line, you can start from here. If you don't remember, then you start linearizing, because they never ask you to prove this. No? Okay, so if I want to find the gradient, this would be 20.0. Can I reach 20.0? 21 can. Minus 0.0. And this one would be a strange scale. Size. Five. 36.4. So this one will be 1.82. Of course, you're going to ask me unit, right? Ln here is unitless. There. This one here is minute. So this lambda is minute -1. Is it SI? No. Wait, I think I'm subtracting wrong. 0.0 minus 20.0. So negative lambda is negative 1.82. Lambda is 1.82. Is it SI? Nope. Do I care? Nope. Because my final answer is in minute, right? So ln 2 over half-life is 1.82 minute -1. So eventually, when I find half-life and I flip the fraction, it will be minute long. So part of the challenge of this paper is to know what you need to do so you don't waste time, and know what you don't need to do so you don't have to waste time. So 0.381 minute. Okay. All right. Next, at t equal to 0, the mass of atom X in the sample is this much, 5.66 times 10 to the power -7. Determine the nucleon number of X. Okay, can. Let's start first by transferring my answer in the right places. Also, I want to think about how can you find the nucleon number and the mass, because hopefully students who did this question before winter 22 will be able to make that connection. Okay. Lambda is negative gradient is 1 mark. I think if you reach here, you'll get 1 mark. Half-life as well. Okay. So whenever they give me something like mass, I know the only way to arrive at this is n. Number of particles. So I write down what I know. No? Number of moles is number of particles divided by Avogadro constant. Or number of particles is number of moles times Avogadro constant. I had to bring in mass. The only way to bring in mass is by thinking about what is molar mass, right? Because I want to find the nucleon number. So the nucleon number is also the molar mass, which is basically mass of 1 mole. Okay. So I probably need to use this. Just write down what we know. It's the first one. Second one, I want to invite mass into the equation. So to find the number of moles, I will take the mass m divided by the molar mass. Because if 1 mole is molar mass, then m is n. Cross multiply. 1 mole is the molar mass, which is also the nucleon number x in gram. Then if my mass is this amount, this is my m. Okay, then I'm going basically trying to find what is the number of moles for m. Okay, so basically what I'm saying is I need to know how many particles is 5.66 times 10^-7. So I'm going to use the handy dandy equation. A is equal to lambda n, right? I know A because I read the activity. Okay, so at t is equal to 0, ln A slash Becquerel, if you want to, you just write the whole thing inside, okay, is 36.4. So you can find A, e to the power of 36.4. Becquerel is also second negative one, but it doesn't matter. So I'm just gonna e to the power of 36.4. So this is a lot. 6.43 times 10 to the power of 15. Okay. Next, I want to use it into A is equal to lambda n. Okay. So this one is 6.4. I look for half-life by lambda, this half-life. Okay. A bit annoying. But anyway, hang on. 6.43 times 10 to the power of 15. I could use the value of lambda that I have just now, or I can go back to my ln 2 over half-life because I need this to be in SI. Okay. Ln 2 over half-life. But this was minute negative 1. Lambda was minute negative 1. Half-life was also minute negative 1. Now. If you can convert, then you convert. No? Either one is fine. N. So I'm looking for N. 3 times 10 to the power 15 divided by 2. So this would be 2.12 times 10 to the power 17 particles. Okay. But this is also 5.66 times 10 to the power -7 kg. So I guess I have to find the number of moles. Okay. So next step, hence the number of moles will be equal to 2.12 times 10 to the power 17 divided by 5.66 times 10 to the power of -7. If you are thinking, why am I doing chemistry? Sometimes in nuclear physics, the nucleus is a chemical element, so we'll be doing some chemistry. But then, wait, this one, the number of, why did I divide by this? My bad. Number of moles is actually N over NA. Hashtag not a chemistry teacher. So 6.02 times 10 to the power 23. How I know I'm wrong? Number looks weird low. This is number of moles, so I shouldn't expect to see weird numbers that are too big or too small. This 3.52 times 10 to the power -7. So now we do ratio, right? Maybe there's an easier way. Can bring this after the fact. So 3.52 times 10 to the power -7 is 5.66 times 10 to the power of -7 kg. But I know in the land of chemistry and molar mass, this thing has to be in gram. So I'm just going to preemptively change this to gram. -7, -3, -4 gram. So now to find the molar mass, this is 1 mole. Okay, and then here I need to figure out like what is this nucleon number? AZ, A, which is also the molar mass. So ratio. So meaning from here, 3.52 times 10 to the power -7 is equal to 5.66 times 10 to the power -4 over A. -7. Don't convert correctly. Checking calculation. -0.0. Oh no, this is not 0. This is 35. Okay, this means brains are tired now. Okay, how do I know? This is 16 something something. This is already off. Something is off. So I trace back. Calculation all checks out. Trace. So you need to check your calculation. Okay, so this means this is not 0.0. During exam, how? I'm not going to delete everything. I'll just rewrite 35.0. You don't have the time. 36.4, 35.0, divide by 20. So this would be 0.07. 0.07. It's going to include another SF. So ln 2 over half-life would be 0.070. 2. So my half-life is actually 10 minutes or 9.9 now. 9.90, 10 minutes-ish. Okay, so everything is fine until here. This is 9.9. 10 to the power 15. Stay calm. Check. Okay, so if I press my calculator, this one would be 5.51 times 10 to the power of 18, making this 5.51 times 10 to the power of 18. Okay, so then this one would be 9.15 times 10 to the power of -6. If you repeat the ratio, which is this one would be 9.15 times 10 to the power of -6. Your A would be 61.8. The closest one would be 62, which is your molar mass. So different people will require different steps, all right? This is the one where I show all the detailed workings. But generally speaking, your nucleon number shouldn't be in the thousands. So if there's an error, don't leave your answer like that. You can trace back one. I mean, it's not ideal, but it's also not really the worst thing to cross out the wrong one and write around it, which is why I recommend people, because in the exam you get a real piece of paper. Then you can space out the working accordingly. Okay, so let's see what we have done. So I know that I want to find the number of particles. So I'm going to use A is equal to lambda n. This one is non-negotiable. Okay, so from here, I can see that my A is e to the power of 36.4, which is this one. Okay, and right now, to find the number of particles, I will take ln 2 divided by half-life to get lambda. And then from here, I can find the number of particles. Okay, I wasn't able to tell whether the answer was correct or not because these two numbers are not that far apart. Okay, so then I can find the number of moles, because if I can find the number of moles, I can find the molar mass. If I can find the number of moles, I can find the molar mass. If I can find the molar mass, I can find the nucleon number. Basically, this is our trajectory. From activity, find the number of particles. From number of particles, find the number of moles. Okay. Then from the number of moles, find the molar mass. Okay. So then what I did was I look for the number of particles and I find the number of moles. 9.15 times 10 to the power -6 moles. After which I use ratio because I know that this much mass, this much particles, sorry, there's not 3.52 anymore. It's not 3.52. This is 9.15 times 10 to the power -6. So I know this much particles is this heavy, but I also need to convert kg to gram because chemistry defines their molar mass in grams. Normally in chemistry lab, you will measure out your elements in grams. It's very normal, okay? So once I convert this to gram, I need to figure out if this many moles is this heavy, then what is the mass of 1 mole? because the mass of 1 mole will be my nucleon number. I use ratio or whichever molar mass equation that you know to arrive at 62. To be honest, I never memorized the molar mass equation in chemistry 1. I understand what is 1 mole and ratio accordingly. But if you have a more familiar equation, you can go ahead. Basically, when the number of moles is 1, the mass is molar mass. I just ratio accordingly. Okay, then the molar mass itself will be equal to the atomic number. So if you arrive here and you feel a number is very weird, like just now, don't be ashamed. It's okay. Double check, trace back. So the key thing here is you want to be able to go through the paper with enough time so that you have time to come back and revisit. Will I immediately check where is wrong? It depends on the timing. If I still have enough time, because this is question 12, okay, it's the last question, then definitely I'll go back and check. But if I have other questions that I want to go to, I can leave it here because I'll still get marks in most of the places except certain calculation. Okay, so the marks for this one is if you write A is lambda n, you will get 1 mark already because you're going to use this to find the number of particles. And then the next thing, if you say that the number of particles, this kind of relationship, number of moles is number of particles over Avogadro constant, you get 1 mark. Okay, and finally, you use a suitable ratio to arrive at the final answer. Dissection is 1 mark. Remember, your nucleon number is always an integer. Okay, please don't write 61.8. Nucleon number is a number of nucleons, how many proton and how many neutron. So it has to be an integer. All right. So is this difficult? Yep. So sometimes you will encounter challenging ones. And this one is a maths chapter, basically. It's a combination of maths, a little bit of physics, and a lot of chemistry. So the only way to get good is to practice well. And because this semester I haven't been teaching A2, so you can see I'm a bit out of practice. But it's okay. You just need to do a few questions before the paper and make sure that the concepts are solid in your brains. Okay, so there's one last thing I want to address before I call it a day. That would be again, if you miss out anything, I'll put the PDF inside Google Drive. Okay. So this is a pretty standard induced EMF calculation question. You are given, again, if you want to flag this one, this will be FedMarch21 P42. So you're given how B flux density, yeah, how B changes over against T, right? Okay, and the question is basically asking you to find the maximum induced EMF. Okay, so if I want to find the maximum induced EMF, I'm going to use the maximum gradient because induced EMF E is proportional to the flux dt. That means induced EMF is equal, it's not just proportional, it's also equal to d flux dt. It's the same. The proportionality constant is 1 for this case. Okay, and for all your cases in your syllabus. So I get to find the greatest d flux dt. So where is the maximum gradient? Here, right? So I will use induced EMF is d flux dt, start from here. But at the same time, flux is equal to NBA. So I find NBA first of all, d dt bracket NBA. Why? Because the gradient of this line is actually dB dt. See, there's a B here, there's a T here. So I need to invite B into the equation, you see. I take out the constants, number of turns is constant, the area of the coil is constant, dB dt. Okay, then I can substitute. E will be equal to the number of turns, 540. The area is, diameter is 6 cm. Fine. So this will be pi 3.0 times 10 to the power -2 square, pi r square, multiplied by the change in magnetic flux density. So the magnetic flux density, you start with 250, you end with 0. Then the gradient is basically how long did it take to drop from 250 to 0. It takes a very short time, right? Here to here. So it looks like the time is 1.2 seconds. Does that answer your question? I mean, I can press calculator later. So if you look for the flux first, this is the flux value at t is equal to 6 seconds. So then your calculation would look like E is equal to change in flux over change in time, which is 0.3817 minus 0, divided by the time taken for it to drop. Of course, you're going to ask me, how do I know I'm supposed to take here? The maximum, no? Take the steepest point, take the fastest change, which is 1.2. Okay, I will pause here. Okay, Mo. Let me know so I can move on to the next one. I didn't use the maximum. Yep. Why you take this front part? You know how to sketch the graph or not for this one? Since we are on the topic of graph sketching. Hang on, maybe I don't crop this one. I should crop the other one. Let's try to practice sketching the induced EMF graph. Okay, for practice purposes. So I think, yeah, let me press my calculator first. 1.2. Okay, this one is 0.32 volt. Now, if I see here, this is 1.2 second here to here. Here to here is 1.2 second. Here to here, coincidentally, is 2.4. So this means if I want to sketch induced EMF, right? At 2.4, 6, 7.2. So between 2.4 and 6 goes without saying the graph is flat, there's no gradient, the magnetic field didn't change, so there's no induced EMF. Okay. So you can see that this one is negative gradient. So according to Lenz's law, if the flux decrease, the current will try to flow in the same direction to compensate. We don't really emphasize this in graph sketching. So even if you draw negative, it's fine, but you can try to be accurate lah. Negative gradient. Induced EMF is negative d flux dt. So negative is positive. Positive 0.32 EMF. What about before that? 0.32 divided by 2 lor. So in this section, it's increasing. Current will flow, EMF will be in the opposite direction to fight the increase. Negative 0.16. This is basically how it looks like. It's also totally fine to draw positive 0.16 and negative 0.32, as long as the sign for the purple section and the green section is not the same. Okay, so it's normal to, then all questions is normal for them to like double the gradient or half the gradient. So it makes the calculation a bit easier lah, but IRL, it may not be the case. Okay, one last one. Question. Where is, what is, okay. So I think for question for the ON 20 P42 question 9, we're going to focus on the graph sketching. So let me show you the scenario. Whenever I see two coil, my brain is transformer, okay, doesn't matter lah. Okay, so power supply, small coil, whatever happened to the power supply will happen to the solenoid, and because they are close together, will also happen to the small coil. So it says here that the supply causes the current in the solenoid to change. So that means the current change like this. Okay, so this is the current in the supply. I, this is your I. So you're asked to sketch the induced EMF. Okay, so to sketch the induced EMF, since they give me such a beautiful graph, I'm going to zoom in a bit, okay? What I want to focus on is the boxes. Before T1 to after T1, it increases, okay? Half a box to half a box, it decreases. So very similar to the question that we have just now, is that this gradient is half of this gradient. This means I am drawing the gradient. If you want to know the link between them, I'll write it down for you later, but give me a sec to paste the graph underneath. So we can compare them. All right, close enough. Okay, so right before T1 and right before T2, the EMF is increasing, which means I need to have a reverse EMF here. One box to one box. And then for T2 is double the value. Okay, no? Double than here. But it has to be half box. So during the exam, if I want my examiner to think that it's half a box, because this paper will be scanned, right? So I tend to like to draw these lines, but you don't draw also, never mind. Just very clearly, use your ruler, don't freehand like me, indicate half a box here. This is double, okay? As long as this is 2 times of this, you are good enough. You're good to go. Okay? Doesn't have to be 2 cm, 4 cm. It can be, as long as it's clear, 1 cm. Okay? So this section here, the gradient is steeper by 2 times. It might not look like it. Check the base. Half a box to half a box. This one is 1 box to 1 box. So it looks like this. And then anywhere else, you just use your ruler. You see here is a bit thicker, right? So you want to try to copy that on your graph as well. Please use a rule. Okay. So something 0, 0, 0, 0, 0, 0, 0, half a box, 0, 0, 0, 0, 0, 0, 0. Wow, 4 marks. Okay, very good. Opposite polarity, 1 mark. Double, 2nd mark. 0 everywhere else, 3rd mark. the boxes are correctly indicated, meaning one box, half box, half box. Basically, x-axis, y-axis, the shape, and the trend. Okay, Mo. So the link here will be like this. Induced EMF is equal to negative the flux over dt. Okay. But flux is equal to NBA. But B is proportional to current. So I can write B is equal to some random constant current. In my notes, I got write the whole equation, but it doesn't matter. B is proportional to I. So B is Ki. So hence, flux will be N Ki times A. But then N is constant, K is constant, A is constant, only thing left is I. Which means if I want to do the flux dt, the only thing that changes is current. So still looking at the gradient of the IT graph. Because in A2 or in A levels, we're always only dealing with one variable. If we do with two variable, multivariate calculus, that is not in the syllabus lah. That's too much maths now. Okay, so that's one. Okay, part two. Part two is the same axis. They replace EMF with VH. Part two, part three. Next part lah, basically. So we're going to replace the Hall probe. This is VH. Okay, so Hall voltage is proportional to magnetic field, but magnetic field is proportional to current. So VH is proportional to I, meaning they will have the same graph. It's the same, just copy. So one box before T1, one box after T1, increase low. I mean, it doesn't really matter what value you use, as long as here to here increase. No current, no magnetic field, no current, no magnetic field. Got current, got magnetic field. Got current, got magnetic field, got current, got magnetic field, got current, got magnetic field until half a box. Current decrease, magnetic field decrease, current decrease, magnetic field decrease, half a box. No current, no magnetic field, no current, no magnetic field. Teacher, are they giving us mark for copying the graph? Correct. So in short, VH is used to measure magnetic flux density. So if got magnetic flux density, got VH. Induced EMF is to measure rate of change of flux. If the flux got changed or the magnetic field got changed, then you will have induced EMF. See this section here got changed, then change low. See this section here got changed, then change low. So this is the three different graph lah. Are you okay? This one can copy. Of course, you may not, if you don't want to do 2 cm, you want to do 2.5 or anything lah. It doesn't really matter. You copy the graph and the time interval is accurate can already. Half a box near T2, one box near T1. Wow, 2 marks, very nice. Any follow-up questions? Okay. So just remember, Hall voltage is to measure whether got magnetic field or not. If no magnetic field, no Hall voltage. If magnetic field increase because current increase, then Hall voltage will increase. Induced EMF is to measure whether the magnetic field got changed or not. Only when the magnetic field change, which is around T1 and T2, those are the points where you will have induced EMF. Okay, so hope that's helpful. Any other thing you want to ask? You okay?